Which device are you the host on?
Am I the host on the one that just shows the video of me looking at the?
That's your phone or your laptop?
No, that's my laptop.
Oh, cause I was going to tell you to go to participants and you could allow us to actually record. Save you the trouble. Yeah.
Keep on forgetting to do that. All right, participants. So we're going to record.
You could have get Rick Darby and Najee Porter, let's say. Yeah.
Najee Porter.
Yeah, Rick Darby.
Rick. Is that Tyreek too?
Yeah, or Joel. You could have get Joel, sir. As well. Any one of them. Any three of them. Oh.
Porter. I'm recording it as well. I'm going to say no, that said allowed to record.
I think you'd have to click more when you go over them name. They got
ask to start video, make host, rename, put in waiting rooms, remove. Make one person able to record already, you know. But
alright. They're not good enough, sir. Not good enough.
Alright. So we make camera record now. Tell you who. Remember. But what you can record. Alright. Before we get into what Laplace transforms are used for, we want to define Laplace transform. So if somebody can tell me what the definition for a Laplace transform of a function f of t, how do we convert it from the t domain to the s domain?
So I think it's the integral of e to the minus st dt.
So it's the integral of e to the minus st f of t dt. It's from 0 to infinity. In a math text, you will see them say it is from minus infinity to positive infinity. But engineers, time start at 0. Time don't start at negative infinity. Don't know what that is. But mathematicians have to talk about the abstract. But we don't talk about the abstract, we talk about the what is reality. And time must start from 0. All right, in certain situations where we're going to talk about time, and we say that time is negative 3, we have to define what that t equal negative 3 means. All right, for example, we know about before Christ and AD. So before Christ time, they're putting the time at which Christ died as a starting point. So everything is after that. If you're a Muslim, then it's Muhammad, and everything is after that. So the Arabs are now in 1260 something. That is the year that so they start counting from 0 at a relative point. But for us, time starts from 0. So basically, why we're interested in Laplace transform is because it turns calculus, integral and differential, into algebra. And we are better at algebra than we are at calculus. We know more about we can solve everything in algebra, but we cannot solve everything in calculus. So I just want to put in context now some of the things that functions that we would be interested in finding Laplace transform for. So the first one, is a step function. And the step function is, if you look at it graphically, it's
I'm not
just.
seeing the screen.
Can I hear you?
I'm not seeing the screen.
Go to the next direct phrase and pin it.
I'll find out again.
Find it?
Yeah, I'm pin it now. Yeah, man.
All right. So now, why are we as engineers interested in the step function? We're not mathematicians. Mathematicians just interested in these things for the beauty of it. Let me be sexist for a minute and say, pure mathematicians look at maths as this. Like I say, I'm being sexist. You can, ladies, translate it into your female domain. We work in different domains. So pure mathematicians think of maths as this very beautiful, sexy girl. Applied mathematicians think of this a girl with money, for example. Enough money. All right. So we are not interested in Laplace transform for the beauty of it or anything like that. We are interested because it is very useful to us. So for example, the step function. The step function simulates a lot of things. For example, if I have a DC circuit and I flip the switch, a 5-volt DC circuit and I flip the switch, then it will get a constant voltage starting from time t equals 0 up until whenever. So the step function mimics that. Or if it's a constant force, like if it's a car traveling along a road and the force on the tire, if it's a level road, then you mimic that with the step function. So the step function mimics a whole lot of things that occur in nature whenever it's a constant value, a steady constant value, steady current, steady voltage, steady force, steady mass. So, and we define our step function. U of t is equal to 1 for t greater than or equal to 0, and 0 otherwise. So that's how we define our step function. So we want to find the Laplace transform of this function, which is equal to 1. Function is equal to 1. So we're going to say f of s is equal to the integral between infinity and 0 e to the minus st. And instead of f of t now, we are going to replace that by the number 1, the t. So we are left to integrate between infinity and 0 e to the
T
minus
greater than or equal to 0?
Huh?
Well, t equal. Oh, yeah, you have t.
Yeah, you have t.
What is t greater? Okay, t greater than or equal to 0.
Mm-hmm. That's equal to 0 everywhere. Oh, sorry. All right. So we are saying now that e to the minus st f of t for the step function is equal to 1. So we're replacing f of t by 1. And so we have this function e to the minus st dt to integrate between 0 and infinity. Now, I've late engineered people losing them shine. I always say the 3 biggest stutters in the world. Chinese, then followed by the Indian, then followed by UTech students, but you're losing the shine. Can you tell me what this integral is equal to? See what I mean?
Yes, sir.
e to the x.
No,
E to the ax over a.
right. But the A over A. So we are looking at integrating e to the minus st dt between infinity and 0. So bearing what we have up here in mind, what is that equal to?
Minus e to the minus st.
E to the minus e to the st over minus what?
Minus 1.
Minus S, sir.
Oh, minus s.
Now we're going to plug in infinity and we're going to plug in 0. So when we plug in infinity and plug in 0 in there, we're going to get, when you plug in infinity for time, it's an exponential function. Exponential function decay with time.
You
So
go to 0.
as you go to infinity, it's going to go to 0. So
No, 1 over minus s. Supposed to be 1 over minus s.
So plug in, you only see one bag of minus s.
R minus 1 over s. That's supposed to be the final answer.
Right. So plug in this, you get 0 minus. When you plug in 0 in here, anything raised to the power 0 is 1. So put 1 over minus s. So the Laplace transform of u of t, 0 minus 1 over s is 1 over s.
Oh, yeah. All right, sorry, go back over the other side. Just finish right
All right. So
before we go any further, hold it right there.
So the definition of the Laplace transform is e to the minus st f of t dt, and we just found it for the step function. Better to look at it graphically than to look at it mathematically. But graphically, it's just a straight line. And we say we are interested in the function because the step function represents any constant value that is being applied to the input of a system. All right.
Sir Fraser, sorry to cut you, sir. A student is asking to let them in the class, please.
Yeah, keep on forgetting that part.
All right, hold it over the other side now, so in the meantime.
All right.
Hold it over the other side now.
Your mouse stop working now. Sorry, 1 second. So the Laplace transform of the step function is 1 over s. So now, the next function that I want to find the Laplace transform of is the Laplace transform of a derivative, f prime of t. Can I move it from over here?
No, wait, sir. Come in.
All right.
All right, sir.
All right. So now, so the next function that we want to find in this short discussion of Laplace transform is the Laplace transform of the derivative of function. So we want to find the Laplace transform of a derivative. Now, first question, integration by parts. What UDV, what's the relationship that is? Run again.
UV minus ED.
All right. So now, we are going to plug for the function. We're not going to plug in f of t because we want to find the Laplace transform of the derivative. So we're going to plug in f prime of t. So everywhere we see f of t, we're going to plug in f prime of t. So that's the integral between infinity and 0, e to the minus st, f prime of t, dt. So let us go. So now, this is my u, and this is my dv. So what is that going to be equal to? If our dv is the derivative, what is v going to be equal to, first of all?
Repeat the question, sir.
If dv is the derivative, f prime of t, what is v? Let me write it out. dv is f prime of t. What is v?
Would that be v?
Eh?
The integral of that.
Integral of that, how would that work out? The integral of the derivative.
So it would have been f of t. Would have been my original function.
Correct. So now, Laplace transform of f prime of t is u, which is e to the minus st, v, which is f of t, and we're taking that between infinity and 0, minus the integral of v, which is f of t, and when I differentiate u, which is e to the s minus st, what is that going to be equal to? And differentiate e to the minus st.
Minus e to the minus st.
All right, close enough. Minus, leave us something.
S.
S. So let me finish it out and then we can write it down. So this minus with this minus makes it plus, and we're going to carry this S outside. So Laplace transform of f prime of t is equal to this here. We can plug in the things inside it. If I plug in infinity for e to the minus st, we previously said it was 0. So let me just put that in. So that's 0 minus. And if I plug in 0 for t here, e raised to the power 0 is 1. And then t, we say we plug in t, everywhere we see t, we're going to put 0. So e to the minus st, that's 1. And that's going to leave f
And get 0.
of 0. More people to let in.
You can disable the waiting room. Somebody wants to come in the class.
Yeah, I just admit that.
Can just disable the waiting room now.
Why you do that?
Alright, look where you come on your screen, you see security. And click security. And then it's the part where it says waiting room, just click it and it's going to disable it.
Okay, try that. Have you finished this and let me try that? Yeah. Alright. So now, we say when we plug in infinity, we get 0. When we plug in 0, we get 1 and then f of 0. And then we're going to get the minus give me plus and put the s outside. So we're going to put the plus s outside, integral of e to the minus st f of t dt. So here's the thing now. This and this is the same thing. It's the definition of Laplace transform. So we're going to write the Laplace transform of the derivative of a function is equal to minus f of 0 plus s, and this thing here now is our definition of the Laplace transform, f of s. We write it down the other way. So our definition of Laplace transform.
Sir, may I be a wallet there, sir?
Alright, we keep it here and then we move over.
Sir, can you go down? Hold it down.
Hold the camera so that all of this.
Yeah, hold it down. Right. Go over the other side, monsieur.
All right, sir, just the last part over the other side.
I mean, I don't just go back over the other side, sir.
Shall I go back over there now?
Yes, sir, you can go on now.
Alright. So we're going to write down.
What it studied? Yes.
Oh, I should point out that this is called an initial condition.
Is F prime that, sir?
Huh?
The second to last period. It's f of minus f of o. Oh.
All right. So now, for the purposes of, we're going to find one more. The Laplace transform of the second derivative. We're going to extrapolate from it. So now, we said that that's between 0 and infinity, e to the minus st, f double prime t dt. And if we do the same thing that we did before, then that is going to be equal to u. This is my u, e to the minus st. B, this is f. If I integrate f double prime, this is my dv. So if I integrate this, I'm going to get f prime t minus the integral of e to the minus st, and that's minus s, f prime t dt. Suppose we add s. So now, we're going to plug that in. This is going to give me 0 minus f prime. If I plug in 0 inside here, I'm going to get this part here, going to give me 1. T is going to give me 0. Plus s, the integral from infinity and 0. E to the minus st, f prime t dt. Now, we already work out the Laplace transform for this. See it up here. So this is going to give me this is minus f prime of 0 plus s, and then we're going to write this back. Sf of s minus f of 0. So, final thing, Laplace transform of f double prime t is going to be s squared f of s minus s f of 0 minus f prime 0. So the Laplace transform of the second derivative is what we have here.
Somebody asked
So maybe those.
What is it?
Somebody have to let
No, man, I'm not saying nobody. Let them in early. Can I move on?
Wait a second, hold it there. Hold it. On the last line. Hold it, sir. Minus S of F4 minus F prime 0. All right, sorry, I do that.
All right. Just a lot of make sure we're not seeing anything on the screen. All right. So now, I want to just make up a little table or a few little tables. All right. Now, I'm writing down the Laplace transform without the initial conditions. I'm saying that the initial conditions are 0. So if you remember, f double prime of t is s squared f of s. So I'm saying f of 0 and f prime of 0 are both 0. So that's why I just end up with s squared f of s. And in the case of the f prime of t, I'm saying that the initial condition is 0, which is usually the case. And I just have s f of s. So I have s squared, s to the 1, s to the 0. So the first question now, 0, 1, 2. So the third derivative, what do you think the Laplace transform would be if the initial conditions are 0?
S cubed F of S.
S cubed f of s. So this is 3, 2, 1, 0. And the integral, now, what do you think that would be? So count with me. S cubed squared, that's 3, 2, 1. This is 0. So what this must be?
-1.
Huh? It's going to be what?
1.
3, 2, 1, 0. So what is going to be?
-1.
-1. So s to the minus 1, f of s, or f of s over s. All right, so we want to talk about the Laplace transform. We want to just make up this little table, so I'm going to use it when we are doing our solution. So let me just add another little table, which we talked about last week. All right. So we talked about these last. No, we didn't. We talked about the derivatives, sir. Let me. So this is equal to, what did we say for the inductor? What V is equal to again? When you have an inductor, what with L, let me.
LDI over dt, sir.
LDI over dt. No, LDI over dt. If we take the Laplace transform, you see that we will get V of s is equal to L and di dt, which is the same thing as f prime. Alright? Same thing as the derivative of the function. So if I have di by dt is equal to the same thing if I take the Laplace transform to the s. Is. The s stands for the first derivative. I will say s squared is the second derivative. So LDI dt, what we can write for the is going to be equal if v is equal to LDI dt, then v is equal to ls. So it's between v and I, just like how we have volt is equal to v equal to I times r. Now we better have volt is equal to I times s times l. So what we do, we write it as like this, S times L for our inductor. And our capacitor last week, what did we say was the relationship?
One over C
1 over C.
The integral
of I dt.
I dt.
dt, sir.
All right. So now, if I have to write this in terms of Laplace transform, the integral is whatever the function is over S. So the function is I. So what do I write it as if I'm writing the Laplace transform for this? Let me do some rough work here. So we say V is equal to 1 over C, the integral of I dt. So V is equal to 1 over C. And we replace this by the integral function by its definition. So that's I over S. So between V and I is 1 over CS. So we write down the resistance in the S domain, Laplace domain as R. Write down the voltage for the inductors, the value is S times L, and for the capacitor is 1 over CS. So we want to write down that this little table for so that now we can look at solving a few problems.
Hold on a second.
Yeah.
I can move on.
All right. So let us talk about how we use the Laplace transform to solve. So take one example. All right, so we want to look at this problem here. There are 5 volt source, 2 ohm, 3, 5, 1 Henry, and we want to write down so if we write down the problem in the time domain,
T power 0
0 plus.
Oh, 0 to plus, okay.
Yeah, little bit after time 0. I'm supposed to put at t equals 0, the switch is closed. To be technically correct. So write it down when you write it down.
Repeat that, sir.
No, I'm supposed to write at t equals 0, the switch is closed. Find I at t equals 0. Put the little plus means after time t equals 0. After you close the switch. All right. So if we were to write using Kirchhoff's voltage law, what would we write in the time domain? This is a 5-volt source, the resistance, capacitance, and inductance. In the time domain, what does Kirchhoff's voltage law say?
IR plus L di dt plus 1 over C integral of I dt equal to 5.
So we're going to have resistance and current, so that's 2I plus 1 over C, capacitance is 3, 1 upon 3, integral of I dt plus L, and L in this case here is 1. So this is 1 di dt is equal to 5. All right, so now taking Laplace transform, we're going to get 2, and with the Laplace transform, we usually write the capital letter for anything. Plus 1 upon 3, and the Laplace transform for the integral is I s over s plus 1, and L di dt is s I s is equal. And here's where the problem always comes in. Well, not a problem, but this is something that we forget. This is a constant. We can deal with it as 5 times 1. Laplace transform of the step function, which is we say is equal to 1 from t equals 0 on. What did we say the Laplace transform of that is?
One over S.
1 over s. So it's 5 times 1 over s. So we're going to make is the subject of the formula. So that's 2 plus 1 over 3s plus s is equal to 5 over s. So is is equal to now, put everything over 3s. 236s plus 1 plus 3s squared. Make sure I'm not writing rubbish. Is equal to 5s, 5 over s. So now, if we carry everything over this, leave is alone, is is going to be equal to 3 5 15s over, this s is in the denominator already. And we're going to put 3s squared plus 6s plus 1. Everybody following so far?
Yes, sir.
Yes.
All right, now I'm going to divide this by 3 so that avoid a whole heap of problems in my life. So I'm going to divide everybody by 3.
They can't cancel the S, sir. You know, the numerator and denominator.
Oh, yeah. True. S cancel the numerator and cancel the denominator. Yeah.
What is this, man? Oh.
Good thing they find out the problem was going to be way harder than it is.
Yes. Mistake.
Give me a second. It seemed like phone run out of battery. Run out of charge. Okay. All right, so while like I said, I'm going to divide everything by.
Wait, what on, sir? No,
No, the phone that you pin.
Yeah.
I don't know if it is protesting on your behalf. Because the plug in and charge it and still run out of charge.
So what a new phone, sir?
Yes.
Okay, I'm going to write that apart then. I'm going to finish right.
Okay, let me try something else. Turn on this.
That's a serious fool, no, sir. Sick man, fool, lick me down, man.
Man, a corona, if you're going to want to say corona,
No, son of that.
You can't taste anything?
Not mom, I can't taste anything.
Taste, not face.
Yeah, man, I know. I can't taste nothing. Those appetite for food, I can't taste anything. But they drink them just pain up, you know?
That means they want to say corona, yeah.
No, corona, because...
Get a lemon, man. You can have some warm water. Man, you get better.
Do what? You need to hear, so that just in case.
Get a lemon. Squeeze it in some more warm water. And go to bed. Man, you get better.
I've been trying to get some lemon and can't get it. I don't know why lemon's so scarce, you know.
Anyway, see the bite, man. If them even sell a $1,000 dozen, just buy it.
Yeah, man, me buy it serious, man, but the problem is not hard to get on it because I normally drink it a morning time for tea, you know, just put all 2 slices and throw hot water on it.
Man, if you have that in your system, you can't get sick. Just
and drink
it straight.
Yeah, man, and drink it straight a morning time and clean the system, man, and build up your immune system. But
why? Engineering alone we doing that, sir. We do medicine too.
We know, we're hearing, we're listening.
Because the people don't know the health benefit of lemon, it becomes hard to find me. I tell you, if I plant the tree. If I plant a lemon tree.
You can use sinkers, sorry.
Right. And a lemon alone, you know. And a lemon alone, you know. That one next thing one name ugly. And the grapefruit and Sibyl orange. I don't know if you know the Sibyl orange. You can roast it.
Yeah, man.
Yeah, man.
Yeah, man.
Yeah, man.
Now take some. Now take a combination of turmeric, ginger, honey.
Yep.
And the other thing them call the kind of bush again. Can't remember the bush again. Guinea hen weed.
Yep.
That weak, man.
Yes, man. That's not weak. A combination of them things there. You know Guinea hen weed?
Yeah, man. My body immune to that, so I can't use that.
But depend some of that.
Anyway, sir, bigger staff safe let with the class, please.
Alright, I'm coming. We just link another device. So we just use something else in the internet. The meeting ID again, 3398599 give me 2 more seconds.
Hey, straight on, but I got the doctor now, because they're going to tell us that thing they have. Stay hard.
Yep.
Yeah, man, you know better than that, man.
Once you can't taste, never taste your corona.
The last, the second semester. Anytime I go too hard, work on school and overthink, I'm gonna get little rest. My body always becomes susceptible to flu. Then in the second semester, I had the same problem. And when we go into the doctor and mention flu, why they have push me and my wife out the door. I say, why are you doing that? Because on take my temperature and all of that. Doctor catch her afraid and push me outside and stay far from me. He said, boy. Say sorry.
You can find the other video with me and pin that, please. With the blackboard, where we did stop. You find it?
I'm searching for it, sir.
Just look for the next diagram phrase or 2 diagram phrases.
Yeah, I see it. I'm pinning.
Alright. So
hold it so.
It's a different device, so.
Sir, look like you have to use that one better than the other one. Camera quality turn up, man.
Well, I was afraid to use it at the beginning because I never know what quality it would have. You test it and then you find out if not really.
What's that, 15S at top?
Yeah, 15S.
SQ plus 6S plus 1.
All right, to divide everybody here by 3. 15, the 15, the 15, the 3, the 6, and the 1. We're to divide everybody by 3. So let me put it over here. So IS is equal to, let me put back the 15 over 3S squared plus 6S plus 1 divided by 3. So that's 5 over S squared plus 2S plus 1 over 3. So now we have to this thing called completing the square. so that we can use the Laplace transform. So let me go to the table of Laplace transform and then we're going to look. Any mathematician out there remember how to complete the square? All right, let me just tell you. It's s plus something squared. And whatever it is this number divided by 2. Whatever this number is, in this case, it's 2 divided by 2, so it's going to be plus 1. So that's the first thing you have to remember. Take this divided by 2. Whatever this number is divided by 2, that is there.
Alright, I got s plus 1 squared minus 2 over 3.
No. So whatever is here, you have to subtract it back out over here. So you have 1, always look at it, 1 squared, so I have minus 1 squared out here. And that is the correct answer that you just gave me. So that is going to be s plus 1 squared minus 2 over 3.
Yes, sir.
All right. Now, we go to the table of Laplace transform. So give me a second. I'm going to switch screen. Okay. Now, when you see there is a table of Laplace transform. And if you look at the one that says e to the minus bt sine b t, only problem is that this one here has a minus and we have a plus b squared here.
Got the big cash there.
Yes, we have to go and get one more psychedelic set of table for this. All right. You just see if we make any mistake here before we launch off. So we have 2 blah 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 s over 3, 3s, 15, 3s squared plus 6s, 236, 3s squared, 15s. Okay. So let me bring up a better table of Laplace transform. A bigger table. So give me a second to bring up the bigger table of Laplace transform. So that is basically what we're going to do. We use the table of Laplace transforms and we look up the answer. So that is how it assists us. Yeah, we will find just give me a second here.
All right, sir.
All right. See it here. All right. Let me share this. All right. You see this number 21? That says E to the A shine. That's what this SIN with the H. Shine BT is equal to B over S minus A squared plus, minus B squared. So this is the function that we are going to use. So basically, we're going to write it down and then make a comparison. So we're going to, let me just write it down and then we see how we're going to move from here. So this is going to be E to the AT SINH BT is equal to B over S minus A squared minus B squared. All right. So we look up and see that this function that we have here and this that we have here, the closest thing that we have to it is this. All right. So now we're going to write our IS as being equal to S plus 1 squared minus 2/3. Now, the B up top and the B squared that is here. So this, if I'm going to write this, I'm going to have to write it as, let me write it as root. If this is 2, B squared is 2 over 3. Then B will be the square root of 2 over 3. Now we want to get back 5. So this will be 5 divided by the square root of 2 over 3. We have multiplied this root 2 over 3 by this 2 over 3 to cancel and get back 5. So I don't know if everybody see what I'm talking about here. I have to write back.
That's fascinating. I
So B
Is a question on sign that?
I entertain fear foolishness now, not right. I make it foolishness sound even more.
Is a greater than sign that?
Somebody can go almost to a phone, but I go make it look like say I world problem just so we just get rid of that corona fully. Single-handedly.
That's it.
All right. So B squared is 2 over 3. So B, this B here, would have to be the square root of 2 over 3.
Is greater than sign that, sir?
Huh?
E to the AT psi or BT equal or greater than that?
No, equivalent to. I'm saying that this is a transform that gives us this function. So now, what is my B in this function? It is root 2 over 3. So what is my A equal to in this function? We compare this with this. What is my A equal to?
The minus 1.
Minus 1. So I'm in the position now to write down what my I of t is going to be. So I of t is going to be e to the a, which is minus 1. So e to the minus t shine bt, which is root 2 over 3 multiplied by 5 divided by 2 over 3. So we can fix that up. 5 divided by root 2 over 3 is the same thing as say 5 multiplied by root 3 divided by root 2. I take this. Oh, pointing at the wrong side. Yeah. So I of t is equal to e to the minus 1 t shine. Shine is just an exponential function, exponential at minus exponential minus at divided by 2. But most people always just find one little word for it instead of writing on the web of numbers. So shine root 2 over 3t, and then we just fix it up this. So we're going to flip what is on the denominator. So the 3 go over the top and 2 go down the bottom. So that's why we have 5 root 3 over root 2, e to the minus t, shine root 2 over 3 t. And that's so that's what the current is going to be, which basically tells an exponent, decaying exponential function.
What other side?
Put it over back over here.
Yeah, what is this?
It's a phrase.
Yes.
If you put it on your calculator and you get the expression without the sign h, and you write it down, it will still mark it right.
If you write down, put it in your calculator, we don't understand.
We give it in terms of the exponential. It doesn't use the sign h.
You give it to, oh, no, not a problem. Not a problem.
What it on first, sir? No, don't. Yeah, we said b equal
root 2 over 3.
All right, a equal minus 1.
A equal minus 1.
What about the other side now, sir?
Sir, I'm not done now.
Oh, sorry. Freeta did done for the class, so when Freeta said, me move.
No, sir, no.
No, well, I wish part Freeta come from. I'm clearing that.
Learn
Trulani. You can't get to know. Which part of Trulani again?
Well, my father said also Spring Alps. I've never been there.
Oh. No. My wife come from Trulani, but we also part of Trulani.
So I don't say what I've heard come from.
Next side, sir. Next side.
Right. That's not what he said. All of the friends of them come from down the side. My wife is married. My wife's cousin is Freita. She married to one of the Freita them. Not you.
Hold on, sir. Freita and Fraser are related.
No. Freita then come from Trulani. This is supposed to be a 5. It's supposed to be a 3.
Oh, let me go something from it for myself. Yeah. All right, yeah. 5 over root 2 over 3. 5 divided by 2, 3, and then I. And we have this, so 5 times root 3 over 2.
Over root 2.
Five times root 3 over root 2.
Yeah.
Is IT that, sir, and LT?
This?
No, the top one.
E to the minus t.
No, man, the top one is LT or IT? Yeah, right there.
I have t. I have a function of time.
All
right, so closing exercise. This one here, we want to write down the differential equation and the transfer function for the system. So measuring x in this direction. Right on the problem?
Yeah. Yes, sir. Yes, sir.
All right. So basically, we have a mass, we have a force F, and we have two. Remember, so this is Kx, and this is BV. So B is 3, K is 2. So I'm going to write 2x and 3v. And this is M. So the net force is F minus 2x minus 3v. And that is equal to the mass times acceleration. That has to be Newton's first law. But M is 10. So what we have is 10A, if we carry this over this side, 10A, sorry, carry these two over that side, plus 3V plus 2x is equal to F. So I said last time that we can write acceleration as d2x by dt squared. We can write velocity or speed as dv by, sorry, dx by dt. And this is 2x is equal to F.
BV.
What again?
Go back over the other side. BV, KX and another BV. Okay, BV. All right.
So if we take the Laplace transform, so this is our differential equation. All right, so if we take the Laplace transform now, second derivative is s squared, and the letter that we're using is s. First derivative is s.
So we're assuming that the initial condition is 0.
Assuming that the initial conditions are 0. Remember to write that down somewhere. Now, the principle of what is called a transfer function is that we take our output x. And our input is the force. So the force causes the thing to extend. And our differential equation, we write down what is called a transfer function. If we write the output, which is the displacement of the mass over the input. So we're going to carry x and put it, carry side f and put it over here and carry everything else over to the next side. So we can write xs over f of s is equal to 1 over 10s squared plus 3s plus 2. That's my transfer function. For the transfer function, output over input. We get our transfer function from our differential. Good.
What is all of sir? 10s squared?
Yeah.
Times x of s?
Yeah. All right. We had a few issues, so the Canvas site will be up next week. Next week we're giving you your first assignment. Not anything too grand from my perspective. I don't know what you are going to feel about.
Sir, our work is really nothing too grand, sir, because
too much stress.
Sir, our teacher mad me.
What's the name of the course? It's so fast.
Engineer economics.
Oh, if I book I read, I go to the University of YouTube.
Sir, not that. The amount of assignment in my gear.
Oh.
You can't even breathe.
Start the course then and everyone will drop it.
Dr. Graham.
Well,
I have to drop it, man, because I'm coming like same in my math people.
Well, assignment, them not bad still in sir. I don't say timing.
No, right now, me have one.
Come like you know, no time to do another course. You have to do that by itself.
Right now, me have one assignment. After this, me can't even look point. Me have to go finish it because it's due tonight.
So what is that after? You have T, F,
transfer function is x
over f of s.
Yeah.
Which is equal to 1 over 10s squared plus what? 3s?
Yeah.
Plus 2.
Plus 2. Well, like I said, I doubt that the assignment will stress anybody too much. Let us see.
Oh, you're posting an assignment?
Yeah.
Okay.
All right. So we're going to stop there for today, ladies and gentlemen. Is there any questions?
Yes, sir.
Mm.
You're supposed to convert back to time domain or leave it like that?
No, when it's transfer function, you leave it like that.
Okay.
Sir, can let's hold the phone look steady there, please.
Okay.
Get that.
All right.
Yes, yes.
All right. So next week we're going to finish our look at differential equations. I'm going to talk about Laplace. Well, we're going to be putting everything together. MATLAB everything, and then we're going to see. We're going to be moving on to matrices. All right, so that's that for today. See you next week.
All right, sir.
All right.
Bless up yourself, sir.
Yeah. All right, Fred.